Hello, Physics Nation. My name is Nate Larmond, and this is the second video to analyze this truss right here. The last time, we just did the geometry of this, the angles, the lengths, and we got cut off finding the torque exerted by this load and the torque exerted by this load and the torque exerted by this load. So torque is just F cross R, so 1,000 pounds applied 3 feet away from the pivot point. We arbitrarily chose the left-hand side of the truss to be the pivot point, is negative 3,000 foot-pounds of torque, and 250 pounds acting 5 feet away from the pivot point is negative 1,250 foot-pounds of torque, and 500 pounds acting 7 feet away is negative 3,500 foot-pounds of torque. So we have 1, 2, 3 negative torques being applied by these 3 loads in the middle of the truss. So this reaction force from roller joint C has to counteract those 3 negative torques. And it's in equilibrium. So if there's no angular acceleration, the sum of these 4 torques must be 0. And that's where we got cut off. So we know 3 negative torques has to be canceled out by 1 positive torque. And that positive torque is provided by the reaction force at roller joint C. And it is 10 feet away. So this is called the lever arm right here. 3 plus 2 plus 2 plus 3 is 10 feet. So it's basically 10 multiplied by this force has to be equal to these 3 torques, the sum of these 3 negative torques. Let's see if I can show you what it looks like algebraically. Okay, so here are the 3 torques I was describing, negative 3,000, negative 1,250, and negative 3,500 foot-pounds of torque. Well, that sums up to negative 7,750 foot-pounds of torque. And like I said, that has to be perfectly canceled out by the positive torque exerted by the roller joint at C. So, like I said, force cross radius, or force multiplied by lever arm, is torque, and roller joint C is 10 feet away. So you just have to do the sum of the torques, 7,750 foot-pounds divided by 10 feet to figure out the reaction force. At this side, the right-hand side of the truss, roller joint C, there is an upwards push, a reaction force of 775 pounds. It's a roller joint, so there is no horizontal reaction force developed on the right-hand side. All right, and where to next? Well, once you know this upwards force, we're going to use another condition of equilibrium. Not only is there no angular acceleration, but there is no translational acceleration. So now we just grab Newton's second law, F equals ma, and we're going to do the vertical version. So the sum of the vertical forces equals mass times the vertical acceleration, but there is no vertical acceleration. These are called statics problems for a reason. There is no motion. This truss is in static equilibrium. The bridge just sits there. Okay, so we have these 3 loads, negative 1,000, negative 250, negative 500 pounds, and this positive 775 that we just found, the reaction force. So we're going to figure out what this other reaction force is. So now, instead of thinking of it as a lever twisting at A, we're just thinking of it as a structure supported at 2 ends. So 3 negatives, these 3 loads, and 1 positive, the reaction force, and this mystery reaction force, a second positive force, all have to add to nothing. Because, again, this thing is in static equilibrium. The sum of the vertical forces is 0. And we just grind through the calculations. The sum of the downwards forces is negative 1,750 pounds, 775 from the roller joint C. That equals negative 975. We add that to both sides, and we get 975 pounds pushing up on the left-hand side. And this sort of makes sense because the loading is asymmetrical. So because we have this bigger force, this negative 1,000 on the left-hand side, we're going to have a bigger reaction force, 975 on the left compared to 775 on the right. All right, what are we doing next? Oh, we're going to zoom in on pin joint C. All right, so this is the far right, right there. So you can envelop whatever system you want. The system boundary is just sort of, a figment of your imagination. It's just a mental construct. You can isolate this member, this joint. We just treated the whole thing as one big mass, but now we're going to zoom in on this pin joint right here. Let's do that. The sum of the forces acting at pin joint C are 0. So this is why we define the geometry of the truss. Where the steel is, that's where the force is too. So we can sort of use our like meter spatial geometry to help out our pounds or our newtons, our force geometry. So we know member EC is 45 degrees below the horizontal. That means the force has to be 45 degrees below the horizontal. And, it's just a little bit of SOHCAHTOA. So the sum of the vertical forces acting at pin joint C is 0. We just found the reaction force to be 775. Well, that means the downwards portion of the compression force in EC also has to be 775 because there are no other vertical forces. So what is the downwards portion? Well, we have to do a little bit of trig. Like I said, sine of theta equals opposite over hypotenuse, except in this case, opposite is the vertical member the vertical portion of the entire force, the compression force in member EC. So we substitute the math language with the physics language. The opposite leg is the vertical portion, and the hypotenuse is the entire compression force. And all we do is multiply both sides by the hypotenuse, or the entire force. So hypotenuse multiplied by sine of theta tells you the opposite. Pardon my sloppiness, but this is the hypotenuse, the entire force. So we do the force in member EC multiplied by sine of theta is the vertical portion. And here's the substitution right here. We start with Newton's second law, F equals ma. The sum of the forces in the vertical direction are 0. We have a positive 775, and then we have a negative, because it's a compression force pushing down on this pin joint, hypotenuse sine of theta. It's the entire compression force multiplied by sine of 45 degrees. Well, sine of 45 degrees is root 2 over 2, or 0.707. We do a little bit of algebraic magic. We're going to subtract 775 from both sides, and then we're going to divide by 0.707, and we find that the compression force in EC is 1,096 pounds. And that's enough for today. It's probably too much. Thanks for watching. See you in the next video.